Okay, let's do some summation simplification examples. We talked about in the previous video why this is important. We talked about how you can change the starting index of these properties if you want to. So make sure you check out the previous video before watching this. So this is your sequence, for your formula for your sequence, but the n is changed to an I, right? So you're taking a sequence, a sub n, and putting it into a summation. You see that? If I have a sequence, a sub n is equal to 7n minus 3, and I want to do a sum on it, either a finite sum to a finite n or an infinite sum, which would be a series. I just put it into this summation and change the n to an I, right? Because this sequence is, let's say, for n is greater than or equal to I, or 1, right? So I put, and it goes, for every integer. So I just say, okay, I is equal to, and whatever the sequence is starting at, 1, 0, -1 to n. Okay, so this is a sequence. Remember that, we're still talking about sequences. Okay, so the first property we can use is this property, which says we can take this sum and separate it into 2. Okay, see that? An AI and a BI, that's just, again, that's just a sequence. 7i is a sequence. It doesn't matter how complicated this is, this first sequence is, or this second sequence is, as long as you're independently summing or subtracting them, you can separate them. So now for this, let's use this property here. So we have a constant, this property here. If we have a constant times a sequence, we can take the constant out. So we can say, and bring the 7 out. Okay, so let's focus. So now we just need to evaluate this here. And we've got a property for that. And again, go check out the previous video to see how this property is derived. But let's just substitute this property in here, right? Exact same thing. So this turns into 7n. Okay, now what do we have a property for this? Yes, this is 3 is a constant. 3 is like C. So this is just equal to 3n. And there you go. This is equivalent to this, right? I mean, this is, put an equal sign here. So if you have an n, I want to say, what is this sequence sum to from 1 to n is equal to 100? Just plug in n is equal to 100 and you get the answer. If you wanted to turn this into a series, so the limit, like if you want to do an infinite sum, so if at a finite n, it's called a finite series or a partial sum of a sequence. The terminology is confusing, but because sequences and series are like kind of intertangled. But if you turn this into a series, so this would be a series. How could you turn this summation into a series? You just say the limit as n goes to infinity of this. Well, I don't know how to take, it's hard to take the limit as n goes to infinity of just looking at this, but I can do limits, and we learn how to do limits in calculus. This is the same thing as the limit as n goes to infinity of this, right? Because this is the S of n. This is the partial sum. Go check out some of the previous videos. It's hard to find partial sums, but if you can use these formulas to simplify your summation, well, these are already proven. You don't need to do a proof. You can check out the proofs for these. You don't need to do like mathematical induction to prove this because we use these properties. So this is an S sub n. If you find a legitimate S sub n for a sequence, then take the limit of that S sub n as n goes to infinity, and that's your series sum, your infinite sum. Okay, we got two, we have an a sub I and a b sub I. An a sub I and a b sub I. Two separate sequences here. So let's separate them, right? This is equal to okay. Now we've got formulas for this and this. This is the I squared, this is the I cubed. So just we're going to substitute, do a direct substitution. So we've got n squared okay, now okay, and that's your answer. Now you can continue, you can keep going to make like your final answer for in real life, really any situation, you want to have the cleanest final answer possible. So maybe if we let's see if we combine these fractions, let's see what happens if we can get something cleaner than this. So yeah, we'll have common denominators. We'll have a 3n squared over 12. Okay, but I'm going to go ahead and do this. And then to make this over 12, it would be 2n okay, now let's see if we can take out an n and an n plus 1. Let's see what that does. And then bring this 12 out here. So let's do, and then, okay, so now we get n plus 1, or no, 3n minus 2. You could argue which one's cleaner. Either answer's fine. Okay, this is interesting. We don't seem to have a property for like an I minus 3 squared, but what can we do? We can expand this. So this is equal to I minus 3 squared is I squared minus 3I minus 3I, and then minus 3 times minus 3. Okay, so now we know how to work with this here. We just separate these out using this property. Okay, now we can take this 6 out, so let's do that. So, okay. So now we've gotten to these properties. So the I squared property is n okay, minus then the 6 times I. Okay, and now that 9 is this property here, so 9n. There you go. Okay, so let's distribute this I. So I cubed plus 4I squared. Now let's separate these into two summations. Okay, now let's bring this 4 out front. And there you go. Now we can just substitute using the I cubed and the I squared. And that's your answer.